All right. Hello, everybody. Hope that you guys are having a good day. I'm, this is a little bit different because it's being recorded. So you're going to have some questions that periodically pop up during this, and go ahead and answer those. And those will constitute our kind of participation grades or participation grade as well as our quiz grade or one of our quiz grades. So I'm kind of anticipating that everyone's going to do, basically perfect on these because it's basically going to set up so that you will have to answer the correct or you have to answer correctly in order to proceed. So, with that said, though, we are talking today about glycolysis. Now, we have a little bit of a foundation for this because we've talked about sugars. And I always like to think about, well, why do we want to learn the structures of sugars? Sure, it's helpful from a like general standpoint of, enhancing your knowledge and expanding your knowledge. But I think that it's also good to think about, well, what's the application? Sugars are a great energy source, but how do we see that? And so we've got glycolysis as a major sugar metabolic pathway for most any and every organism. Now, our learning objectives for this, we're going to define like the overall purpose of glycolysis. So, purpose. And we're going to talk about basically what we get out of it. We're going to talk about glycolysis broken down into two different phases. The net reaction of glycolysis, even though it's a metabolic pathway, there is an overarching or overall reaction. What are the 10 enzymes in glycolysis? And some of these are consolidated, or I kind of consolidate them down. Um, Recognize the three irreversible steps of glycolysis. I would argue that these are if you're thinking like, I need to prioritize some steps of glycolysis, these three are going to be the ones that you want to prioritize. We're going to talk about tissue-specific glycolysis. And what I'm talking about there is we're going to be comparing hexokinase and glucokinase and how they're utilized in different parts of your body. ATP yield from glycolysis, like if we input one glucose molecule, what do we get out of it? And then we're going to explain the role of NAD+. This is a molecule known as nicotinamide adenine dinucleotide in glycolysis and basically how it's, kind of what's its purpose. So the first thing that we want to tackle is the overall purpose of glycolysis as a central metabolic pathway that converts glucose to pyruvate, and in the process generating ATP and NADH. So just as a little bit of a refresher, here's our glucose molecule. Now, if you're looking at that and thinking, okay, well, we had a couple of different types of glucose that we looked at. For starters, this is none other than the Haworth projection of glucose. So in addition to this being the Haworth projection, which I really believe that it's very helpful to number your carbons, just as a little bit of a reminder and refresher, this is carbon 1, 2, 3, 4, 5, and 6. We've got a 6-membered ring here. 5 of those members are carbon. Now, this carbon number 1, if you remember, that's our anomeric carbon. And there's a significance to that being an anomeric carbon or that being identified is because that is a new chiral center. And this anomer, I'm going to erase the IC, this specific structure of glucose is the alpha anomer. Okay. Now, what I think is really helpful for remembering is and being able to quickly kind of redraw or identify the structure of glucose is to look at our hydroxide groups on carbons 2, 3, and 4. And I'm going to erase 5 and 6 because we don't care too much about those. But 2 is down, 3 is up, 4 is down. And that's the significant terminology for the Haworth projection. So with glucose, we're going down, up, down on carbons 2, 3, and 4. And carbon number one, we have our hydroxide group pointing down, which is indicative of the alpha anomer. Now, what glycolysis is doing, and what we're going to do with glycolysis, is take this six carbon molecule, the six carbon glucose, and we are going to make two three carbon pyruvate molecules. Now, this structure, I always find it helpful to redraw it and look at my carbon chain. Okay, there's my two carbons. But one, I've got a carbonyl oxygen, and then the other one, I always like to redraw the angled or kind of change the angle of my bonds because for some reason, whenever I look at pyruvate here, I always see it as like, oh, it's like my mind plays a trick on me and says, okay, pyruvate is one, two, three, four carbons. And then I take a second glance and I'm like, wait a minute, is that a carbon? No, that's an oxygen. So we've got a carboxylic acid or a carboxyl group, a carbonyl, and then a methyl group. So I think that, when you give yourself a little reminder like that, it's helpful. So we've got six carbons from glucose that are being broken down into two identical pyruvate molecules. Now, along the way, the central hallmark or the significant part of glycolysis is that we are investing a couple of different things. I mean, we obviously invest the six carbons of glucose, but we also have to invest some ATP or adenosine triphosphate. We have to invest some PI or inorganic phosphate, some ADP, adenosine diphosphate, and NAD plus, also known as nicotinamide adenine dinucleotide. Now, with that plus, I want you to think back to Gen Chem 1 and think about, let's go with potassium. I'm just using this as an atom. And what we know about potassium as a group 1 element is that it tends to lose an electron. It gets oxidized. Oxidation is loss of electrons, and it forms this K plus. Okay, so this K would be the reduced form, and K plus is the oxidized form. So I want you to think about that, the oxidized and reduced form. The oxidized form is going to have a positive charge. The neutral is going to have no charge. The neutral with no charge is the reduced form. So I bring that up because this is the oxidized form of NAD+. That's part. So we have to invest the oxidized form of NAD+, or the oxidized form of NAD, also known as nicotinamide adenine dinucleotide. Then what we're going to do is we're going to recover. With glycolysis, we're going to recover ATP and NADH. And then, of course, we're also going to recover two pyruvate molecules. Now, the ATP and NADH, well, that's adenosine triphosphate and nicotinamide adenine dinucleotide in the reduced form. So that's kind of if you're thinking about what's the important part of glycolysis, it's that. Glucose is invested along with ATP, PI, or inorganic phosphate, ADP and NADH plus, and then the outcome is we get to recover ATP and NADH, as well as the two three-carbon pyruvate molecules. So I always like to think about, well, if our input is a six-carbon molecule and our output is two three-carbon molecules, are we losing any carbons? No, we're not. We are ultimately just kind of moving around some electrons, and we're, basically doing some oxidation reduction reactions, or an overall oxidation reduction reaction. And that's how we're generating a high energy compound or high energy compounds like ATP and NADH. Now, the entire overview of glycolysis is shown here. So our input is glucose, and then the output is pyruvate. Whenever you look at this model that's displayed here, it's important to recognize right around here what takes place. Well, there's a little bit of a fork in the road, and that fork is where our six-carbon molecule gets split into two three-carbon molecules. So with that in mind, basically everything from here down, think about that as, yeah, that's being produced, but 2x, which is why we see kind of this pathway or this road. And adjust my drawing there, this virtually identical road. Okay, so that's going to sum up the purpose of glycolysis. And so in from there, what we're going to do, so glycolysis is a complicated pathway, and there's a lot going on. In order to, I think, distill the information down as best as possible and most easily extract the like big picture from it, or to, to go from the big picture down to the details, I think our next learning objective helps do that. And that is to break glycolysis down into two different pathways or two different phases. So the first phase is commonly known as the investment phase, and the second phase is the payoff or the return. So we've got the preparatory or investment phase and the payoff or the return phase. Now, it is significant to recognize where that stops and where it kind of, or where each phase begins and where it ends. So we're going to begin our first phase. This is our investment. And I will go into some of the details with the investment phase. But whenever we say investment, it's not necessarily the investment of glucose, but instead it's the investment of this molecule right here, adenosine triphosphate. Now, an important takeaway is, well, what's the purpose of the overall process? Well, the purpose is to generate ATP. But this, I think people like to characterize it as, well, you got to spend money to make money. So we're spending or investing ATP in order to get ATP out. So if you're thinking, well, what's the end point of the second phase? Well, generating ATP is part of it. So in the first phase, we're going to invest ATP, two of them. Now, you can kind of think about this as we're putting phosphate onto our glucose. And that first step, hexokinase, which we'll go into more detail on that in a little while, but that's where we are investing ATP. We're transferring a phosphate group from ATP onto glucose to make glucose 6-phosphate. That's our first investment. Our second investment is another enzyme known as a kinase. So we've got hexokinase, take that term right there and look at the suffix kinase. Then we've got another enzyme, phosphofructokinase, also known as PFK, and specifically PFK1. So these two enzymes, they transfer phosphate from ATP onto something else. Hexokinase, well, we're transferring phosphate onto a 6-carbon sugar. Then phosphofructo. Well, fructo or fructose is a 6-carbon sugar. Phosphofructo, well, or if you think about phosphofructose, that would be a phosphorylated form of fructose. So we're transferring our second phosphate group from ATP by the enzyme PFK onto fructose 6-phosphate. And so that's where we get this molecule right here, FBP, which is a doubly phosphorylated form of fructose. So this is a 6-carbon molecule, 6 carbons plus 2 phosphates. Now, the second to last step, or it's almost the last step, but it's not quite, is an enzyme known as aldolase. Aldolase is an enzyme that breaks our 6-carbon molecule into 2 3-carbon molecules. One of them is a 3-carbon sugar known as glyceraldehyde 3-phosphate. The other, because we're splitting this asymmetric molecule into glyceraldehyde 3-phosphate, which is this one right here, and another enzyme or another sugar known as dihydroxyacetone phosphate. So GAP and DHAP. And if you're curious about like being able to identify all the different components, I am absolutely fine with you knowing just the acronyms, because if you really enjoy this, which this is a part of biochemistry that I absolutely love, you're going to go on to take a metabolism class, and then you'll get deeper into the weeds of all of this. But for our class, if you understand kind of the, not necessarily the survey level, but if you understand by like the acronyms, you're going to be in good shape for this. There are some that are enzymes that we're going to go deeper into. And we'll get back into those after, or I'll specify those in a little bit. So with aldolase, we make two distinct and different three-carbon molecules. One is glyceraldehyde 3-phosphate right here. And what I want you to notice about this is, let's see, we've got, oh, that is a carbon going to or it's a carbonyl carbon with a hydrogen and then an R group. This is an aldose. And then we've got a carbonyl carbon at carbon number 2. That's a ketose. So one of the ways that I always like to think about this and what's helpful for me to remember GAP and DHAP and being able to identify them is to go back to that name. GAP is glyceraldehyde. So you should probably be looking for an aldehyde functional group. Then dihydroxyacetone phosphate, well, that acetone, well, that's indicative of a ketone. So we're breaking an aldose, or breaking our 6-carbon molecule into an aldose and a ketose. Now, the very last step in the investment phase of glycolysis is to take that DHAP and make GAP. So at the end of the investment phase, we have 2 glyceraldehyde 3-phosphate molecules. So that's where our 6 carbons are. We've got 2 identical molecules. Okay, now what that means is if our investment phase stops or concludes with 2 3-carbon molecules, that means that our return phase begins with 2 3-carbon molecules. So I think that it's helpful to break the pathway or the process or the pathway down and look at it like this, because then we can see that we've got, here's one GAP, here's another GAP. Now, everything that's happening here is done basically twice, accounting for all 6 of our carbons that we started things out with. So we've got our glyceraldehyde 3-phosphate molecule, but we've got 2 of them. And for each one of them, we have this reaction taking place. Let me erase that. And this enzyme is going to be adding a phosphate. Okay, now I'm going into a little bit more detail right here than I want to, so I'm going to take a step back because we're going to talk about each enzyme in just a moment. But we start out our return phase with 2 glyceraldehyde 3-phosphate molecules. We're going to invest in organic phosphate and NAD+. We're going to do that twice. We're going to invest some ADP. We're going to then begin recovering or returning. We're going to return our NADH, ATP, and then more ATP. So since all this is happening 2 times, well, there's 2 steps where we're generating 2 ATP. So our total return will be, I've got it highlighted here, return 2 ATP. And then this isn't a typo. I have it twice because we're returning 2 ATP twice. So we're getting a total of 4 ATP out of this. Now, what we're going to end this entire pathway with and the return phase of glycolysis is pyruvate, our 3-carbon molecule with a methyl, carbonyl carbon, and a carboxyl group. That's pyruvate. Now, next up is we need to summarize the net reaction of glycolysis, including the reactants, products, and the energy that's produced. Okay, so here are all of our reactants. We've got glucose. We've got adenosine diphosphate. We've got inorganic phosphate, NAD+. Now you might be thinking, oh, but what about the ATP? The key word here is net. Think back to Gen Chem 1 when you talked about ionic and net ionic reactions. If something is on both sides of the reactant, do you count it? No, you don't. Which hopefully on the next slide will make a little bit more sense for some of the numbers. We're going to get, again, our net products. We're going to get 2 pyruvate, 2 protons, 2 water, 2 NADH, and then 2 ATP. Oh, but wait, I just said that we get 4 ATP. Well, the key word there is net. Our net return from all of this is going to be 2 ATP. So what that ultimately lays down as is what's shown here. Our overall reaction is glucose plus 2 inorganic phosphate plus 2 ADP plus 2 NAD plus, and it's going to yield 2 protons, 2 NADH, 2 H2O, 2 pyruvate, and 2 ATP. Now, just to hammer this point home as it's important, well, how much ATP did we invest? 2. How much ATP total did we return? We returned 4. So if there's 2 ATP on the reactant side and 4 ATP on the product side, well, we eliminate that, and then we reduce that number down to 2. This is, again, just kind of going with the net reaction sort of thing. Um, okay, so this is your big takeaway. Glucose plus 2 ATP or 2 ADP plus 2 inorganic phosphate plus 2 NAD plus yields 2 protons, 2 H2O, 2 NADH, 2 pyruvate, and 2 ATP. Now, the important part about all of this, which we'll revisit again at the end, is NADH and ATP. These are both high energy compounds that are essential for this. Okay. Now, with that in mind, looking at our learning objectives again. Okay, so next up is our 10 key enzymes in glycolysis, as well as their respective substrates and products. Okay, so I think that the important part about this is tracking, well, what is each enzyme doing? So we're going to dissect, looking at our entire pathway, we're going to dissect each member. So our input is glucose, 6 carbons. And this is showing, again, our alpha glucose, that alpha anomer. And then our return is 2 pyruvate molecules. So we start with 6 carbons, we end with 6 carbons. Along the way, we make a bunch of stuff. Now, this enzyme right here, what I want you to notice about it is this is an enzyme known as hexokinase, also known as HK. Now, magnesium or Mg2 plus is essential for this because what it does is it helps stabilize ATP. Okay, so we've got glucose plus ATP, the enzyme hexokinase. Oh, look at these equilibrium arrows. Now,
Aren't you to get these levels for me?
Now, with that in mind, so those equilibrium arrows, well, the equilibrium for this reaction so strongly favors the forward reaction. So going from glucose to glucose 6-phosphate, that this is considered an irreversible reaction. Now, there are a total of 3 irreversible reactions, which we'll look at those individually in just a little while, but consider hexokinase or HK to be one of your first irreversible reaction. Now, and there's some terminology that I want you to be comfortable with that I will go through in just a little while, but we've got HK or hexokinase that is going to transfer a phosphate group from ATP onto glucose to make glucose 6-phosphate. Now, this is an irreversible step. Our next step is going to take glucose 6-phosphate. Again, remembering our numbering on our carbons, this is carbon 1, 2, 3, 4, 5, and 6. That's where we put a phosphate group. What this enzyme is going to do, this is known as PGI. This is an isomerase. All that this enzyme is doing is rearranging carbons. So glucose is rearranged to make fructose. Okay, so all that we're doing is just sort of shifting things around. Nothing major. Now, this is our second reaction, our second enzyme, PGI, phosphoglucose isomerase, rearranges. Our next enzyme is phosphofructokinase. And actually, let me go back for just a second. Look at the equilibrium arrows for this. Completely reversible. We just as soon as we make fructose 6 phosphate, the equilibrium is going to shift back and forth. Which are we making? Which are we breaking? Or not breaking, but which are we making and then which are we unmaking, more or less? Our next enzyme, PFK or PFK1, phosphofructokinase. Again, this is a kinase. This is our third step. Looking at the equilibrium arrows, this is an irreversible step. Now, in addition to this being irreversible, so this is our second irreversible step, there's another term that we use for PFK, which is first committed step of glycolysis. As the first committed step of glycolysis, essentially what that means is that the previous steps, hexokinase, which makes glucose 6-phosphate. Glucose 6-phosphate can go in a couple of different directions. It could be used for different pathways, which we'll see in the coming days. So it could go in different directions. Fructose 6-phosphate also could go in a couple of different directions. It doesn't have to go through glycolysis. When you make fructose 6-phosphate, that can be used for a bunch of different things. It's not committed to be going or to go through glycolysis. Whereas the product of our first committed step, or what you might also know this as, is fructose 1,6-bisphosphate or FBP. FBP is basically committed to go through glycolysis. It is committed. Those carbons are committed to be broken down into 2 3-carbon molecules. Okay, so here is our second irreversible step. But it is the first committed step of glycolysis. Now, our third or our next step, which nears the end of the investment phase, is the enzyme known as aldolase. Now, what aldolase is going to do is it's going to take this 6-carbon molecule, fructose 1,6-bisphosphate. Notice how it's being shown as a linear molecule. That's significant because what are we going to do? We're going to take this 6-carbon molecule and break it into 2 3-carbon molecules. We're going to break it into our aldose, hence that aldehyde functional group, and our ketose, hence the ketone functional group. So we're making glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. This right here, this glyceraldehyde 3-phosphate, that's the one that we want. Now, what that means is we have to rearrange the carbons of glyceraldehyde 3 or carbons of dihydroxyacetone phosphate. Now, I want you to recognize the equilibrium arrows here. That's a reversible reaction. So we have 4 reactions. 2 of them so far have been irreversible. 2 of them have been reversible. Notice there's only 3 irreversible steps. This is not one of them. Our 2 irreversible steps are the 2 kinases that we've talked about. Okay, so what we need to do is now take this dihydroxyacetone phosphate and rearrange it to make glyceraldehyde 3-phosphate. Triose phosphate isomerase, or TPI, is going to do that. It's going to rearrange this molecule shown on the right. It's going to make this ene diol intermediate, and it's going to make glyceraldehyde 3-phosphate. Now, if you're, again, what I've talked about a little bit, and I alluded to earlier, what do I want you to know? I want you to know kind of the acronyms for the enzymes, and I want you to know the substrates. This ene diol intermediate, I don't want you to stress about that and be like, oh, which one has an ene diol intermediate? This is something that you'll go into a little bit more depth on in metabolism, because then you'll be talking about, well, what are the intermediates? What is the mechanism that's being carried out here? Okay, so once we have 2 of these, we've reached the conclusion of our investment phase. So if you think about your investment phase, it's GAP, where we have our two kind of end goals of our investment phase. Because now what we're going to be able to do is take those two glyceraldehyde 3 phosphate molecules and carry out a couple of different reactions so that we can generate ATP and NADH for that matter. So the first enzyme that we're going to do, we actually kind of combine these two together, is we're going to take glyceraldehyde 3 phosphate, and sometimes you'll see this GA3P or G3P or GAP. This enzyme known as glyceraldehyde 3 phosphate dehydrogenase, it's going to make NADH, and it's going to make 1,3-bisphosphoglycolate. Okay, that is immediately going to be used with the help of phosphoglycerate kinase to generate an ATP. So we kind of package these together. We've got this inorganic phosphate that gets added to our aldehyde functional group. That gets added there, and now we have a doubly phosphorylated molecule that we can then use to transfer a phosphate group off of it to make our first of our kind of returned ATP. So at this point in time, at the conclusion of the enzyme phosphoglycerate kinase, we've effectively kind of returned our investment. And we've got NADH. Now, is this the end of glycolysis? No, it's not. But this is a good point to be at where, okay, cool, we've returned stuff. So here what we have is the 3PG, or 3-phosphoglycerate, which has only one phosphate. So we've undone, or effectively we've returned the initial investment of the 2 ATP because remember, this is happening 2 times over. So from here, what we can do is we can go on to our 3-phosphoglycerate, the molecule that came from our previous step. Oopsies, oopsies. And we can isomerize it. We can rearrange the atoms that make this up. Looking specifically at carbon number 2 on 3-phosphoglycerate, we have a hydroxide group. And we're not going to go into the reaction mechanism, but this enzyme basically takes a phosphate and moves it from carbon 3 to carbon 2. And we end up with 2-phosphoglycerate. So we've gone from carbon 3 to carbon 2. Now, from here, what we're going to do is I always like to look at the products here. The enzyme is enolase. Phosphoenolpyruvate is our product, and our other product is H2O. So effectively, what we're doing is we're taking 2-phosphoglycerate and we're removing water from it. How are we removing that water? Well, we've got this hydrogen right here and this hydroxide right here. We're going to remove that, and in the process, we're going to put a double bond between carbons number 2 and 3. The phosphate is staying where it was. Then that will give us our phosphoenolpyruvate, which is a very high energy compound. Now, there's been a couple of high energy compounds that we've dealt with: ATP, NAD, and NADH. And now we've got phosphoenolpyruvate. This is going to use our last of our kinase, or our kinases. We've got pyruvate kinase, which, if you look at the equilibrium arrow, and just so you guys can have a little bit more context and think about the context, let's jump back. Enolase, reversible. Phosphoglycerate mutase, reversible. These two enzymes, glyceraldehyde 3-phosphate dehydrogenase and phosphoglycerate kinase, both are reversible. So this last step is our last irreversible step. And in that process, we take phosphoenolpyruvate, ADP, and we're going to make ATP. We're going to remove that phosphate from phosphoenolpyruvate and add it to, or move it from phosphoenolpyruvate onto ADP to make ATP and pyruvate. So those are our 10 steps in glycolysis. Now, what I want you guys to focus on is I want you to focus on, well, be able to know the sequence of the enzymes, be able to know the overall picture, really have an emphasis in a strong understanding of the reversible steps versus the irreversible steps. The irreversible steps are important because those are kind of going to be your determinants. Those are going to be ultimately some sort of a regulator. Now, with that in mind, we'll go on to our next learning objective. Recognize the three irreversible steps of glycolysis. They are hexokinase or glucokinase, phosphofructokinase, and pyruvate kinase. And what's the regulatory significance? So here's our overall rundown, and here are the three steps. I've kind of organized these in a backwards way, and I apologize for that. I'm not sure why that happened. But hexokinase and phosphofructokinase. Let me actually go ahead and pause and rearrange these. So here we are with our first step, hexokinase listed first or shown first. Um, and that's glucose going to glucose 6-phosphate. Fructose 6-phosphate to fructose 1,6-bisphosphate is our second irreversible step. And this is also, and I really want to stress this because this is an important question. I always love to ask this question. This is our first committed step of glycolysis. Now, keep in mind, irreversible does not necessarily mean that it's a committed step. So the first irreversible step, say first IRR. Now, glucose 6-phosphate. Why is this an irreversible step, but not the first committed step? Well, it's an irreversible step because the energetics of it, going from glucose 6-phosphate to glucose, simply is not favorable. Now, why is it not the first committed step? Well, it's not the first committed step because glucose 6-phosphate can go in any number of different directions. Our first committed step is fructose 6-phosphate going to fructose 1,6-bisphosphate. Now, our last overall step is our last irreversible step, and that is pyruvate kinase. So I want to highlight this, that we have a total of 4 kinases. 3 of them are completely irreversible. The last of them, phosphoglycerate kinase, which I draw your attention to right here, well, that is a reversible step. Now, a fair question of that is, well, why? And a kind of blunt answer is because, well, your compounds that are involved in phosphoglycerate kinase, everything's a high energy compound. So 1,3-bisphosphoglycerate and 3-phosphoglycerate, those are both high energy compounds. And so using them to either make ATP or, going in the opposite direction and using ATP, those are both favorable reactions. So what I would recommend is knowing my kinases in sequence and remembering hexokinase is my first overall step. It's my first irreversible step. My next irreversible step is the third overall step, but that's also my first committed step, and that's phosphofructokinase. My last step overall is my last irreversible step, and that is pyruvate kinase, where we're making the last of our ATP. Next up is be able to describe the role of glucokinase and hexokinase in glucose phosphorylation and how their activities differ in different tissues. So here what we have is, basically your typical cell. We've got hexokinase, which, well, hexo. That enzyme is going to be able to basically take on any 6-carbon sugar and phosphorylate it. And it has a Km for glucose of approximately 0.1 millimolar. So it can grab onto glucose and no problem whatsoever. Whereas in the liver, down here, we have glucokinase expressed. So what that means is that is going to be very selective. It's not going to see fructose and be like, phosphorylate. It's not going to see mannose and phosphorylate. Instead, what it means is that enzyme is going to be looking only for glucose. Now, one thing I'd like to draw your attention to is it has a Km of approximately 10 millimolar. Now let's think back to the Km and let's think about affinity. A high Km means relatively low affinity. Okay, so between hexokinase and glucokinase, which one of these enzymes has a greater affinity for glucose? Well, that would be hexokinase, which is kind of, wait a minute, then what's so special about glucokinase? Well, one of the reasons, and I think that whenever I explain the reason, it helps the explanation for understanding why glucokinase is special a little bit more um, easy to grasp. So, in our typical cells, think about that as like, muscle cells. Basically, any and every type of cell in your body is what it's doing is it sees glucose and it's like, great, energy source. I love it. Now let's compare that to the liver. What the liver is going to do is it's going to be basically making sure that your body or that there's enough blood in your blood, or sorry, there's enough glucose in your bloodstream. And so you don't really want glucokinase to be like, ooh, glucose, I'll process it and metabolize it. Instead, what you want is the liver to basically be like, hey, I need to maintain a glucose concentration of approximately 5 millimolar. So, do you want the liver to be able to break down glucose? Not really. You kind of only want it to break down glucose whenever there's a lot of glucose. And by having a Km of approximately 10 millimolar, well, it's really only going to turn on and activate whenever the glucose concentration in your bloodstream is really high. What you want is you want your liver to be there to store glucose and basically keep an eye out and say like, okay, is there enough glucose? Yeah, we're good. We're good. So between these two enzymes, hexokinase and glucokinase, which one of them can act on glucose very quickly? Hexokinase. Between the two of them, hexokinase has a lower Km, therefore it has a greater affinity. Glucokinase has a high Km, therefore a lower affinity than hexokinase. And that's fine because glucokinase is basically exclusive to your liver, which is what you want regulating and making sure that there's not too much uh, blood or glucose in the bloodstream. There we go. I was about to say blood in the glucose stream. Okay, so our second to last one is actually a little bit simple. Calculate the ATP yield of glycolysis, the investment and the payoff phases, and compare it under aerobic and anaerobic conditions. Now, first of all, I think that it's fair to, or one of the ways that makes this a little bit more complicated. Actually, for the moment, I'm just going to say, what's your takeaway for ATP and NADH production from glucose? Well, the net is 2 ATP. Why is it 2? Because you invested 2 and you returned 4. Well, done. You invested 2, and then this step right here, PGK or phosphoglycerate kinase, repaid that. And then you had pyruvate kinase, which paid it back again. In which case, that's where you ended up with a net of 2. A total was 4, but your net was 2. This is a place where you got to be kind of careful and maybe hesitant or maybe cautious and judicious whenever you're looking at the questions that are being asked. Okay, now NADH, well, we're not investing any NADH, but we're getting NADH out of this. We're investing some NAD plus, but that's all there is to it. Now, with that in mind, when you look at all of these different steps, and you think about aerobic conditions or anaerobic conditions, well, aerobic are going to be oxygen rich, and anaerobic would be oxygen depleted. Is oxygen as an atom used in these compounds? Yep, 100%. Is oxygen O2 used in any of these reactions? Nope, not a single one. So glucose, in terms of aerobic or sorry, glycolysis in terms of anaerobic and aerobic conditions, well, you're not going to really see any difference there. So anaerobic and aerobic conditions, effectively the same. Now, next up, what I want you to think about with respect to these is let's say that instead of glucose being a fuel source, let's say you were able to like mainline in some fructose 6-phosphate. Let's say that, the next time you went and got Cheetos or something like that, it said sweetened with fructose 6-phosphate. What do you think that would mean in terms of like the ATP that you're going to extract from that? Well, the energy that you would extract from that right here is your jump in place. You're bypassing this first reaction. In which case, or what that means is you have a little bit less ATP investment. So, if you were consuming something that had just an astronomical or I don't know, just a high amount of fructose 6-phosphate, you're jumping in there. I apologize. You're bypassing that glucose step. You're bypassing that initial step. In addition to that, you don't have to do the PGI. So hexokinase and phosphoglucose or phosphoglucomutase isomerase, phosphoglucose isomerase are bypassed. So you don't have that investment, in which case your net ATP return would be a little bit greater. Now, the last thing that I think is important to think about is if you've taken a biology class, whether it's a cell biology class or maybe like um, maybe if it was a biology class in high school or something like that, um, there are some other parts about this. What did we end glycolysis with? Well, with glycolysis we ended with pyruvate. What else? NADH, ATP. That's about it. Now, if we are looking to get a lot of energy, what's the energy currency of a cell? ATP. Okay. So then how do these other things like NADH and pyruvate, how do they play into ATP generation? Well, that's what this last item is about. There's something known as the electron transport chain. Like I said, if you've taken a cell biology class, you probably learned about the Krebs cycle, also known as the tricarboxylic acid cycle, also known as the TCA cycle. Um, and that is a cycle that is going to take your pyruvate and help you extract a ton of NADH from it. It's going to help you completely oxidize that pyruvate. So this is going to be TCA. And it's going to be TCA basically so that you can make a bunch of NADH. That's not the only compound that you're making. You're making some guanosine triphosphate, some ATP. So it's still valuable in that sense. But that pyruvate and that NADH, that's going to fill up an NADH pool. And this is the electron transport chain. And what I want you to know at this point in time about this is that you're going to put in NADH. What are you going to get out? ATP. That's the entire point about this. Um, so that's really the important part about this pathway and what we're going to do with these different products from it all. Okay, well, that's where I'm going to go ahead and wrap it up. I hope that you guys enjoyed this, and I hope that you have a good one. All right, thanks everyone. Bye.